So now we will talk about acid-base titration. And for the acid-base titration, we have a strong acid was titrated with the strong base, weak acid titrated with the strong base, strong acid and the weak base, and the indicators, acid-base indicators. Okay, let me just put the slideshow. Okay, so this one, so let's go to the strong acid and strong base titration. So first of all, the process of titration. In chapter 4, we introduced titration, and you did perform 2 titration lab in Chem 11. And so you should be familiar with the process or the lab procedure called titration. If not, visit chapter 4 and find that part about the titration. And well, in the titration, we have a titrant and we have an analyte. The titrant, it's a solution that is added from the burette. And normally the titrant will be the one which we do not have the concentration. We do not know the concentration. And analyte, we put it in either in a beaker, like we have on the picture right here, or in an Erlenmeyer flask. We will add the analyte solution. So if I have a strong acid and strong base, the curve, the titration curve, will look like this. So let's analyze this graph. So on the x-axis, we will put the volume of a base, strong base, and NaOH added in the milliliters. On the y-axis, we will put the pH. And as you can see that when the volume of NaOH or a base was 0 ml, the pH in a beaker or in an Erlenmeyer flask, it was 1.0, I believe. So from here, you will understand that in the beaker, we had an acid, and the NaOH was in the burette that was added to the beaker, and the beaker contains the acid, and that's when, as you can see here, when the volume of NaOH was 0, the pH is very acidic. It's 1. So as we add, you see this is the volume of NaOH. It was added from the burette into the beaker. We're adding the NaOH. And as you can see, at the beginning, the pH does not change that much, So it was the 1. Even if we had 10 ml of NaOH, the pH is slightly bigger than 1.0. So we're adding pH, and at some point, as you can see over here, when we added 25 ml of NaOH, we can see the pH was drastically rising from pH about 2 to pH like around 12. So this is the curve, represents the titration curve when we have a strong acid that was titrated with a strong base. At the equivalence point, meaning we have equal moles of acid and the base, equivalence point, equal moles of acid and the base. At that point, the pH of a strong acid and a strong base is 7. Very important to know this graph. So now let's take a look at this. Let's say we are adding 0.1 molar NaOH solution from a burette to a vessel, a beaker, Erlenmeyer flask, which has 25 ml of 0.1 molar HCl. We will be writing a chemical equation for that. And then, so you know that this is the strong base, which will completely dissociate into an A plus or H minus. This is a strong acid, H plus Cl minus. This is a salt, and it's an ionic compound, also completely dissociate into an A plus Cl minus ion. So at the equivalence point, you can see OH minus plus H plus forming H2O. So this is also, you can look at the chapter 4 and review chapter 4, the acid base, the reaction between acid and bases, or neutralization reaction, the net ionic equation for that. So now what they're asking us to calculate the pH of the solution at every stage of a titration. So let's say prior to the addition of a base. So prior to the addition of a base in a beaker, we only had acid. We simply can calculate the pH of a strong acid. And pH of a strong acid, you see this is a strong acid, the concentration of a strong acid 0.1 molar, and we know it completely 100% ionizes into H plus and Cl minus. So that means the concentration of H plus is also 0.1 molar. Since we know that, we will put this in the pH equation, which equals to the negative log of a concentration of H plus, and we can see that the pH of the acid is equal to 1.00. So this is the 1.0. This is a pH of the acid before any NaOH added to that. Now, let's say, what is the pH before the equivalence point? So let's say we added 10 ml of 0.1 molar NaOH to that 25 ml of 0.1 molar HCl. So now we can find moles of the acid and the base, or we can find millimoles because I have milliliters, and using millimoles instead of moles will simplify our calculations. And remember that millimoles equals molarity times ml. So because molarity is mole over 1 liter, but if instead of 1 liter I will put 1000 ml, then I can calculate the moles. So do you see I can cancel ml, and I will get milli. I will put millimoles over milliliters, and I will get millimoles. So before the equivalence point, when I'm adding the 10 ml of NaOH solution, the total volume of the solution will be 35. Don't forget I have 25 ml of HCl, and I added 10 ml of NaOH. And now I want to find the number of millimoles of NaOH, first of all, in 10 ml of this 0.1 molar solution. So I would say 0.1 molar solution is 0.1 millimole over 1 milliliters. Then I will multiply by 10 ml, and I will be getting 1 millimole. So the moles of NaOH in 10 ml is 1 millimole. So this is the 1 millimole. So now we can calculate the number of moles or millimoles of HCl that are originally present in 25 ml of 0.1 molar HCl. So I will say 25 ml, and so this is a molarity, and I will get that moles or millimoles of HCl is 2.5 millimole. So out of that 2.5 millimole, 1 millimole will react with the NaOH that is added. And after that, I will not have any NaOH left in the beaker, but I will have 1.5 millimole of HCl in a beaker. So once I have that, so do you see I have 1.5 millimole of HCl, but the volume of my solution is 35 ml. 25 comes from the acid and 10 ml comes from NaOH. So I can find the molarity of my HCl solution, which equals to this number. And since this is a strong acid, the concentration of H3O plus also equals to this number. And I can calculate the pH of the solution when 10 ml of NaOH is added, which equals to 1.37. So now the equivalence point. So we have equal, as you can see, equal moles of H plus and OH minus. So let's say we will add 25 ml of 0.1 molar NaOH to 25 ml of 0.1 molar HCl. This is a complete neutralization reaction. And at that time, all the H plus from the HCl will completely be neutralized by all the OH minus coming from 25 ml of NaOH. And what we will have in that solution, in that beaker really, we will just have H2O, water. Because don't forget that for acid-base reaction, net ionic equation is H plus plus OH minus makes H2O. So at that point, at the equivalence point in the beaker, you have a water, H2O. And we know that at that, let's say, room temperature, the pH of the water is 7, or the concentration of H2O plus equals to the concentration of OH minus, and it's equals to 10 to the negative 7. So that means the pH of a solution is 7. So now we can add, we're adding more NaOHCl after the equivalence point. So now let's say we're adding 35. We see this is 35 ml of NaOH. We're adding to this 25 ml of HCl. Again, we need to calculate how many moles or millimoles of NaOH we added. So we will take this 35 ml of NaOH multiplied by molarity. We will get moles or millimoles. We already know how many millimoles of HCl we have. Then we can say we have 2.5 millimoles of HCl in that original 25 ml solution. And that amount, 2.5 millimoles of HCl, will be completely neutralized by NaOH. And at the end, we will have extra NaOH remaining, 1 millimole of NaOH remaining. Then we can find the concentration of NaOH. This is 1 millimole dividing by 60 ml. You will be getting, this is the concentration of NaOH. And then we can find the concentration of OH minus. Yeah, this is a concentration of OH minus because it's a strong base. NaOH is a strong base, and the concentration of a base equals to the concentration of OH minus. And we can find POH. And from that, we also can find the pH, 14 minus POH. So now you can see now in that beaker, now we only have base and the pH is 12.22. Okay. So they were calculating millimoles over here, as you can see. But if you want to liters to liters, you can find moles. You can actually work with the moles, or you can work with the millimoles. It doesn't make a difference here. So now the second type of a titration, when we will have a weak acid, but we're titrating in the strong base. So take a look at this graph of the titration curve. When again, in a beaker, you have I'm sorry, this is a strong acid, this one. So in a beaker, we have acid, and in a burette, we're adding drop by drop, we're adding a base, which is NaOH. Take a look at this graph. This graph is different than the graph for a strong acid and a strong base. At the time, but we did not add any NaOH. The amount of the NaOH is 0. The pH is not very low. It's about 3 pH, about 3 pH. But if you look at the strong acid, at that moment, when not NaOH is added, no NaOH is added, the pH is very low, which that's one of the differences. The pH is high because it's a weak acid. The second difference is at the equivalent point, the pH is basic. The pH is 8.5, where the pH of a strong acid and a strong base at equivalence point equals to 7. So this is the two big differences you have to notice here. At the beginning, the pH is higher because it's a weak acid. And at the equivalence point, the pH is also is high. It's not 7, it's a basic pH. That's a second difference. So now let's do the same calculations and find the pH before the base is added, before the equivalence, before the base is added, before the equivalence point, at the equivalence point, and after the equivalence point. So let's say we have a base. This is a sorry, acid. This is a weak acid, and this is a weak acid. This is acetic acid, and this is a strong base, sodium hydroxide. So we're getting a salt formed and the water. But this is a prior to the addition of a base. We did those calculations before, how to find the pH of a weak acid. This is really, we did cover that before. So you will say, okay, this is my weak acid. Weak acid will form hydronium ion, and it will form the conjugate base. Then the reaction will reach the equilibrium at initial concentration of the acid is giving to me. I do not have initially the products. That means reaction will shift to the right, minus X. That amount of the acid has to be consumed. This is how much of the hydronium ion and a conjugate base will be formed. And this is the equilibrium concentration. So just adding those two components together. Yes, and we have a Ka for the acid, 1.8 times 10 to the negative 5. So once I have that, I will put the expression for the Ka, and I will find that the x squared equals 0.1 times 10 to the minus x, and it equals to the Ka value. But when we will be, again, as you can see over here, we simplify this expression 0.1 minus x. We'll say about 0.1 because Ka is very small, and we are solving for the x, and the x is the concentration of a hydronium ion. And when we will put this into the expression of the pH, we will find the pH of that weak acid is 2.87, and that's what we will see over here. So what is the pH before the equivalence point? Somewhere over here. So when we add the base, where we have a little of a base, some of this acetic acid will be converted to the this acetate ion. And we can actually use the Henderson-Haselbach equation to calculate the pH. This is a pKa of this acid. Then the logarithm, this will be the, this is what we're adding. We're adding 10 ml over base. So if we're adding 10 ml over base, then the solution will have 1.5 millimole of acetic acid and 1 millimole of acetate ion. Let's go back and we will see what we have here. This is the concentration of the, let me go back over here. So we have a 0.1 molar of the acetic acid. So we're adding 10 ml of the base. We're adding 10 ml of the base, and the solution will have 1.5 millimole of acetic acid and 1 millimole of acetate ion. We will put it into the Henderson-Haselbach equation, and we will calculate that the pH will be equal to 4.56. This is prior to the, this will be prior to the equivalence point. So now at the equivalence point, so at the equivalence point, all the acetic acid will be neutralized, and what we will have left, we only will be having acetate ion in the solution. And if we have an acetate ion is a conjugate base, right? So it's a conjugate base, and the pH of that solution now will be determined by this acetate ion, which is a conjugate base. And what we need to do, we have to find the Kb of the acetate ion. So now the equivalence point is added when we have 25 ml. Yeah, I do not believe they talk over here that this is why I was trying to find this out. What they have over here, the weak acid and the weak base, they failed to mention that the volume of the acid, we have a 25 ml, because then you will wonder where we're getting those numbers. So the volume of ml. And this is why over here we're getting 1.5 millimole left. So we have 10 ml of the base, and that solution will have 1.5 millimole of acetic acid and 1 millimole of acetate ion. So now this is the equivalence point. So at the equivalence point, we added 25 ml of a base. And as you can see, the total volume is 50 ml because 25 ml of a base is added to 25 ml of acid. Okay. So all the acid is gone. And we will have 2.5 millimole of acetic acid has been converted into the acetate ion. You see the acetate ion. And so now we will find the concentration of this acetate ion, 2.5 millimole over the total volume. And we will have the concentration of the acetate ion, which is a conjugate base, is 0.05 millimole. Molar. So then you have a base, and the base will react with the water. As a base, it has to take H plus from the water, accept a proton, will form this acid back, and OH minus. The concentration initial is given to us. We'll put the ice table. The Kb for the acetate ion you can find. Don't forget Ka times Kb equals to Kw. You will find the Kb. You put everything into this expression, and then we will find the X, and the X is the concentration of OH minus, and we will find the POH, then we will find the pH, 8.72. So at the equivalence point for the weak acid and a strong base, you have in the beaker of conjugate base, weak base, and that base make the solution have a higher pH, which is like 8.72. It's a basic pH, really. We have a basic pH. So we can do the same calculation after the equivalence point. So after the equivalence point, when we are adding a strong, we are adding all the weak acid is gone, and you have a strong base. So when you're adding a strong base, there is nothing in the solution to consume any additional OH minus, and your pH will be determined by the concentration of the OH minus, which is coming from the strong base NaOH, and that will be between 12 and 13. So, and that's just, they're giving a different volume and the concentrations. So this is a sample problem. I hope you will read the textbook also. Look at the textbook, chapter 17 on ALEKS, and look through these problems. They're giving solutions to that as well. So try to calculate those pHs before, after, before the base is added, before the equivalence point, at the equivalence point, and at the equivalence point. So this is a similar, absolutely similar work here, similar titration, but what is happening here? Do you see what is happening at the beginning when well, first of all, we're adding HCl. From the burette, the HCl is added. You see volume of HCl added. So that means HCl is in the burette, and in our Erlenmeyer flask or in a beaker, we have a base here, because at that point when no HCl is added, the amount of HCl is 0, we have a very high pH. It's a basic pH. So that means in the flask, Erlenmeyer flask, a beaker, you have a base and you're titrating a base with acid. So, but what you have a weak base. You have a weak base, because if it was a strong base, it will have a higher pH, about 13.5, about 14 probably. So we're titrating a weak base with a strong acid. Strong acid is HCl. So pay attention to that. Why it's a weak base? Because not a high pH. At the equivalence point, you have acidic pH. It's about 5.5. It's acidic pH. So that's the two things you have to pay attention to. So take a look at the titration curve, analyze the titration curve, and you see they're saying the HCl is added. That means in the flask, in a beaker, they have a base. This one is added from the burette. So that means you have a base, so you have to have a basic pH. Not a very high pH, that means it's a weak base. So if it's a weak base, at equivalent points, a weak base will form a strong conjugate acid. So that strong conjugate acid at the equivalence point will make the pH slightly acidic. So let's take a look at all of those calculations, try to understand those calculations. Here they took a strong acid HCl. As a weak base, they took the aqueous solution of ammonia. It's ammonium hydroxide. And the same calculations at the equivalence point, after the equivalence point. Take a look at those and try to understand this.